Okay, hello and welcome to my channel. Today we're gonna take a look at problem 1, set 2 from MIT OCW course 805 Quantum Physics 2. Right, so let's begin real quick. Let's skim through the requirements and what is given here. So you're given an infinite square well with a delta function inside. Okay, right, this guy here, v of x, and 0 to a, this delta function is right in the middle, so a over 2. Your v of x is v naught a delta x minus a over 2. And you're given something here. Gamma is defined as v naught over h bar square over ma square. Right, and this guy is a lot greater than 1. Okay, and now you're asked to calculate. So you calculate E ground and E1. Include correction of order. So you have to do a series expansion and then compare. G and E1. Right, cool. You're given as normal psi at 0 and a is equal to 0. Your psi of x is a sine kx and a sine k a minus x into interval here from 0 to a over 2. So the first half of the well. Next one is the second half of the well. Right. Okay, so first of all, you can easily spot that doesn't matter what you, which side you take. What you're gonna get is that your psi of x is gonna equal to a sine k a over 2. This is for every region inside the well. So we can say that continuity is satisfied here. So continuity should probably split this into 2. Okay, so continuity at a over 2 plus is going to equal to a over 2 minus to psi ka over 2. All right, so that's what we have. Now let's take a look at the discontinuity in the derivative for the delta function. Okay, so x0 minus psi x0, this is plus and minus to 2m v naught a, or alpha. V naught a is alpha, the intensity of the delta potential. Okay, and psi at 0. Right, so let's do the derivative now, shall we? First one is ka cosine ka over 2. Second one is another ka cosine ka over 2. Right, and that one is 2 v naught a square a sine ka. Okay, this is what we have. Now this term, we're gonna put them together, get 2ka. Well, a don't really have to consider that, but just put it here for now. Not a over h plus square, a sine ka. Right. So from here, what we're gonna do is isolate this term. So we're gonna isolate this term by dividing everything by a sine k. Wait, this is ka over 2. Right, divide everything by a sine ka over 2. Okay, so after we do that, we get 2k cot ka over 2 equal to 2mv naught a for h bar square. All right, so now we're gonna put this term over to isolate our cots. And do that. The 2's gonna cancel. So no. Get our cots and then try to put everything into gamma since we do need gamma. Okay, so let's check out. This looks pretty similar to our gamma up here, right? So see what we have. The minus sign is there. We have m v naught, m v naught a square. So we have to put an a down. K stays. H bar square cancels. All right, yeah, I think this is correct. Right, so now we have gamma, and we want to, well, we have the word compare here, so and series. So try and see what is interesting when you let gamma goes to 0 or infinity. And gamma here you see is proportional to V naught, meaning that if you let gamma goes to 0, you just get a generic infinite square well potential. So nothing interesting there, meaning that this time we're only going to consider gamma going to infinity. So we're going to get 2 separate well, since when this delta potential increase to a point, it's going to split these two into 2 separate well, or decouple this well. It just sounds more fancy. That's basically what it means. So we're gonna let our gamma goes to infinity. So now that means our minus gamma over ka is gonna go to minus infinity. So what now? We have our cot. Cot goes to minus infinity. That means what inside is, well, pi with an argument. So we have ka over 2 is going to be an argument of pi, meaning, well, pi with a slight nudge in the face. Right, so what is a slight nudge in the face? Basically, you have ka over 2 is going to equal to pi o minus delta with delta very small. That is a nudge. Okay, so cot of pi minus something. Think about the rules of trigonometry. You have, well, here we learned that, well, pi minus alpha is going to equal to minus cot alpha. So apply it for the above. Get that is equal to minus cot delta. So now we calculate delta. Yeah, so what do we have here? The 2 over. We're gonna put this in a series. So minus gamma sum of gamma, yeah. Good. Gamma, the pi, this term factor out. The other term is pi, this all minus 1, 1 minus, the other term is delta. There's a 2 here, alright. Guess, I think that's correct. Okay, so we got our series expansion here that we can do. That's the only reason why you put the minus 1 there, because you don't really want this in the denominator. Okay, so minus cancels, good. Now this is gonna equal to 2 pi 1 plus order of square, since we're only need the first order of the series. That's good. Right now we can do something with this expansion. Okay, so we have this guy very small, so cot is also going to equal to 1 over delta. Infinitesimally small. Cot delta is also going to go to 1 over delta. Okay, so that is very convenient for us. So we're going to take the gamma over 2 pi. Over here is going to be equal to this. Right, so take that 1 over delta is going to be equal to gamma over 2 pi. Alright, so here you get that your delta is going to be 2 pi over gamma. Good. Okay, this is gamma. There we go. Okay, so we did find the delta. Now we're gonna find something that satisfies the requirement, which means that your series have to be in order of 1 over gamma. And pi, delta here is already containing your gamma. You can just substitute and do the thing. So let's find k equal to pi over minus delta. Yes. Now we get k. Okay, so k is 2 pi over a 1 minus delta expand is going to be 2 over gamma. Right, so we have this. The ground state energy. Ground state energy is gonna be h bar squared k squared over 2m. We can put this like that. The square, we're gonna take out the square, so 4 pi square. Okay, we square a times this square, we can put it in another expansion. So this one is kind of confusing. Put it in an expansion and only take to the first order. Right. Okay, and E1 is n squared pi squared h bar square over 2ma square. yeah, since we're taking the infinite square well. So that is one first excited state is 4? No, 2. N square is 2, right? No. Wait, what? Yeah, that's, no, that's 2. 2, so n squared is 4. H bar square pi square over 2 ma square. This I'll rewrite as 2h bar square pi square over ma square. Right, so this can also be rewritten as that. Okay, so write it down here to be more, well, neat. This is 2h bar square pi square over ma square. 1 minus 4 gamma. 1 is just 2h plus pi square of ma square. Right, so you can see that our E1 doesn't have any gamma dependence. So we can compare these by minus. We'll take these two and minus each other. So that would just be the gamma dependence term, which for 8 square pi square gamma a square gamma. Right, so this is our difference. And last question is what is happening to the energy difference? So see that we're taking gamma to go to infinity here, and if we let gamma goes to infinity, the difference is going to be 0, meaning that, well, your ground state energy is going to be equal to the first excited state energy. So degenerate happen. And why is that? Well, this is the mathematical proof of this, but I think you can also see this physically. First is, why are there no gamma dependence in E1? So you take state, the first excited state, there is one node at 0, meaning that at that point it is 0. So it doesn't really care about that, the delta function. So there are no dependence there. But the ground state is even, so it does care. So that one is going to be the one to change. Okay, so when you put the energy, when you sketch the energy out, since the first excited state doesn't depend on gamma, it's going to stay the same. So you can sketch it as like a flat line, just a constant. But your E ground does change because it depends on gamma. So it's gonna be rising. So E ground is gonna be rising. It's gonna rise to something and then plateau. It's just plateau here. It's just gonna approach this line, doesn't cross it. And this line is E1. This is your E ground. So that is like some physical insight to this problem, but really you don't need to do that. You can do that if you want to understand the problem a little bit deeper, but if you're just finding exercises to do, then the only thing matter here is the mathematical part. So that's it for today. Goodbye.